All right now. So what I'd like to do in this screencast is I'd like to do 6 examples of volume questions that on the surface may look similar, but in reality they are very different questions. So let's set it up. We're going to let R be the region bounded by y equals x over 2 and y equals radical x. So that means here's y equals radical x. Here's y equals x over 2. So this is the region R. We're going to do 6 volume questions that relate to that region, which I am going to group together and decide to clone. Let's put all of this together so that I can copy this when I need it. Excellent. So let's make this the base of a solid, and the cross sections perpendicular to the x-axis are squares. So when we see cross sections, we start thinking about, okay, what's the area of a square? The area of a square is side squared. There's going to be a little thickness perpendicular to the x-axis, and we're going to integrate that from start to finish. Where do these two curves cross? The blue curve crosses the red curve at 0 and 4. I'll let you figure out why that is true, but it's definitely 0 and 4. So what's the cross-sectional slice here? The cross-sectional slice here is the vertical distance between this and that. So when we take cross sections perpendicular to the x-axis that are squares, the Triscuits have dx thickness, and then one side of the Triscuit goes from the blue curve to the red curve. And so that is our integral that gives us the volume. Fundamental theorem gets us home from there. We're not interested in that. We're just looking to set things up. So let's, let's take that same region and let's take cross sections perpendicular to the y-axis. If we take cross sections perpendicular to the y-axis and they're squares, then we're still integrating side squared, but we're taking perpendicular to the y-axis. We're going to do a dy integral. And how long is this side of a Triscuit anyway? Well, it goes from the red curve to the blue curve. So we would do red minus blue, but we need them in terms of y. So if this is y equals x over 2, then getting x by itself, that's 2y. And if this is y equals radical x, then x is y squared. And so we have red minus blue from bottom to top. Red minus blue squared, because it's a square, from bottom to top. Then we want to take that region R. I'll just slide some of these further down. I want to take that region R, want to rotate it about the x-axis. If we rotate about the x-axis and we take a vertical slice, then that vertical slice is perpendicular to the axis of rotation. And when we're perpendicular to the axis of rotation, we go with washers. The bigger radius goes from the x-axis up to the curve that's further away. And the little radius goes from the x-axis to the curve that's closer to it. From left to right. If we were to rotate about the x-axis, we would use washers, pi radius squared minus pi radius squared. But if we rotate about the y-axis and we do a vertical slice, then that vertical slice is parallel to the axis of rotation. And if the vertical slice is parallel to the axis of rotation, then we use cylindrical shells, 2 pi times a radius times a height dx. What's the radius of a cylindrical shell? It goes from the axis of rotation out to this x value. How high is the cylindrical shell? Well, it's the difference between the function values. How do we do this? We distribute the x, find an antiderivative, sub, and subtract. But that's not our concern. We're just looking to set up the integral in this case. So 2 more to think about. Want to think about what happens when we rotate about the line x equals 5. Here's x equals 5. And then we want to talk about what happens when we rotate about y equals 5. This figure is very not drawn to scale because this is at y equals 2 and that's y equals 5. But there is a gap and you get the idea. If we take a vertical slice, as we try to, because that gives us a dx integral, that vertical slice is parallel to the axis of rotation. And when the slice is parallel to the axis of rotation, we use cylindrical shells, 2 pi, radius, height. The height is as it ever was. But what's the radius? Well, the radius goes from the axis of rotation to this x value over here. From the axis of rotation to this x value over here. From the axis of rotation to that x value over there. 2 pi, radius, height, thickness. When we spin about y equals 5, take a vertical slice, and we take a vertical slice because it lets us do a dx integral. Well, that vertical slice is perpendicular to the axis of rotation. And if that vertical slice is perpendicular to the axis of rotation, we have pi times big R squared minus little r squared. That's how this goes. What's big R? Big R goes from the axis of rotation to the curve that's further away. From the axis of rotation to the curve that's further away. From the axis of rotation to the curve that's further away. And then what's little r? Little r goes from the axis of rotation to the curve that's closer. From the axis of rotation to the curve that's closer. We don't have to evaluate the integral, we just have to set it up. We made a slice that was perpendicular to the axis of rotation, and because the slice is perpendicular to the axis of rotation, we use washers. Washers is pi big R squared minus pi little r squared. I hope that this is helpful. These are the 6 flavors of how volume questions come to us. Please reach out with questions. I will be as helpful as I know how to be. Thanks for watching.